Okay, continuing with address types. So we were discussing the network address, broadcast address, and the available IP addresses, the range of available IP addresses that we can have. So I took an example of a network 192.168.10.0, which is basically what we have here. And you realize what we call the broadcast IP address is where we have the host portion broadcast. The host portion is all ones. That is what we call a broadcast address. So this is what we mean by all ones. You take the host portion and every bit that you have on the host portion, you put it to 1. And after this, you realize this is where we get our 255, which is our broadcast IP address. Then 256 plus 1 is supposed to be the next network ID, but since we have a /24, we are not going to have a 256. Then for the available addresses, which is basically the range, we'll start at here. This is .1, this IP address. This is .1. Then it ends at 1, 2, 3, 4, 5, 6, 7, 0, which is 254. So the range of available IP addresses, we are starting at 192.168.10.1, and we are ending at 192.168.10.254. This is the range of IP addresses that we can assign within this network. And if we want to send a broadcast to every device in the network, we use 192.168.10.255. These are the IP address types that we have. I think you definitely need to get used to calculating IP addresses, making use of conversions of decimal to binary. Right. IP address calculation. What are an example? What are the network address, broadcast address, and what are the network address, broadcast address, height, and number of available addresses of class B 172.16.10.1.16. So this is another example that we are going to go through basically. 172.16.10.1.16. Let me see, 10.1.16. So our ID 172.16.10.1/16. We want to find what is the network ID, what is the range of IP address that we can have, and what is the broadcast address. So how do we find those? Number one, you start by identifying the network portion and the host portion. The network portion, we identify it by using this prefix length. So if I have 16, it basically means the first 16 bits of my IP address identifies my network portion. So in Katasa 16 bits, where do we have 16 bits? These are 8, these are 16. So 172.16 identifies my network portion. Then everything after that becomes zeros. So this is my network IP address, network ID. Why is everything after that becoming 0? When I'm looking at the prefix length and I say 16, how to find this IP address? You end the value of 16 ones with this value. So basically, you are taking in 172.16.10.1, and you are ending it with 16 bits or ones. So if I put 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, then I put 8 ones here. This is 8 plus 8, 16. And I have 0 here. There's 8 zeros here. So this is 8 zeros like this: 1, 2, 3, 4, 5, 6, 7, 8. Then I put 172 in binary, I put 16 in binary, 10 in binary, 1 in binary. And if I end these two values, what I get basically, if I end 172 and 8 ones, I get that same value. If I end, when we say end, this is basically what we did in logic. 1 and 1 gates, that's 1. Then 1 and 0, that's 0. That's the end we are talking of. So if you end these two values in their binary form, what you basically get is 172, 16. Then if you end any value with 8 zeros, you get a 0, you get a 0. That's where we are getting this value. So to identify your network ID, you just end your IP address with your subnet mask or prefix length, whichever is the easiest way for you. Then from there, to identify our broadcast IP address is probably the next simple thing. To identify the broadcast IP address, like I said, host portion or ones. That's how you identify the broadcast. So if I take my network ID 17.172.16.0.0, this is the host portion. So this is the network portion, 16 bits. This is the host portion, 16 bits. And if I turn the host portion into all ones, what I get is then this 1, 2, 3, 4, 1, 2, 3, 4. What is the value that I have here? This is 255. This is 255. So my broadcast IP address is 172.16.255.255. This is my broadcast address within my given network. To find the broadcast, you just use the host portion. All bits in the host portion becomes ones. That's how you identify the broadcast. Then to find the range, you can see my IP addresses will go from 172.16.0.1, which will be the first address in the network, to 172.16.255. Then here we have 254. This will be the range of IP addresses that we can have. How do I find that? If I have a 0 here, it basically means 1, 2, 3, 4, 1, 2, 3, 4, all zeros. Then the first bit will become a 1 here. This identifies network era .1. Then I have .2, .3, .4, up until I get .255 here, 0.255. Then this 0 also starts changing up until I get 254. Then if I add 1, I'll go and get my broadcast IP address. So the relationship basically becomes, if you are given an address like this one, if you're given an address like this one, you have to find the network ID. To find the network ID, you end this value with its prefix length, which is 16. And I think this is the process that was being done here. So you are ending, this is 172, this is 16, this is 0, this is 1. And you end it with these 16 bits. So I have 8 bits here, I have 8 bits here. And if I end, I get this value here. What is this value? Is 172.16.0.0.16. To get my broadcast ID, all ones, these are the all ones or my host portion, in the host portion and ish. And if I put all ones, what do I get? This is the value I get. That is my broadcast. And to find the range of IP addresses that are available, I start with a 1 here. That gives me this value here, 172.16.0.1. Then all these values start changing up until I get 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7. I cannot get a 1 here because it becomes a broadcast, so I get a 0 here. In this value and this upper, this is the value which is representing this. And that is basically how we find the network ID, the broadcast ID, and the range of IP addresses that we can use in a given network. Private and public. Now, when we're discussing private and public IP addresses, you realize that I think I say this in every class, we have a set of addresses. Excuse me, we have a set of IP addresses that we call private. What are private IP addresses? These are addresses that are assigned to a given network. How do I put this? These are addresses, private addresses that are assigned to a given network. Then public IP addresses, these are addresses that are used over the internet, basically. Right. So let me give an example to explain what public IP address and private IP address is. Let me see if I can pull this off. So private versus public. Very important to understand this. So if I have this is my local area network at home. So this is my home network. IP addresses in my home network are private. If I have another person here at their home and so home too, IP addresses here are also private. If these two networks once want to connect to the internet, their private IP addresses will need to be converted to a public IP address. So basically, private IP addresses are addresses that we use in our local area networks, and public IP addresses are addresses that are used for the internet. The reason why we do this is best explained by the exhaustion of my IP addresses at Agwit. So we cannot have a scenario where every device has a unique IP address. In this case, you can have, for example, here an address root 192.168.10.10 within this network. Kunok may be not on this router, but on another network. You can have another IP address which is the same as Yandai. So what does that mean? For the same IP address which is private, I can have many private local area networks using that same address, meaning my address is Edo. We can use multiple addresses at the same time. However, this is within our local area network only. Now, internet, that address will need to be changed into a unique public IP address, which is unique over the internet. So this one will change. This one will also change over the internet. These two, 1 and 2, cannot be the same over the internet. So you realize private IP addresses are addresses that we use for our small networks that we design. But as soon as we want to connect to the global network, which is the internet, then that private IP address will not work. It will need to be converted to a public IP address, which will be used over the internet. So you can see these are the set of IP addresses that we have. These are private. So this is our small network with a private IP address, private IP address, private, private. But as soon as we want to get into this area here, which we call the internet, those addresses will need to be converted to public IP addresses. All right, special addresses. We also have my special addresses. Let me start with the loopback. We have a range of IP addresses, these ones. which are used to test if our devices are operational. So it's basically an IP address which is used to send a packet to a device to itself. How do I put this? A device. So if this device router wants to test if it is operational, it sends a packet to itself. Sending a packet to itself basically means using these IP addresses. So if it sends a packet to itself and it receives it, then it means the device is operational. So it's usually sort of a self-test, and it uses a loopback IP address. Any IP address, these are usually addresses which are used if you want to send a packet to any device in a network. It matches any device in a network. This is a limited broadcast IP address used as a destination address for all hosts. We have a link local address, usually used to give an IP address to a device which has failed to be addressed either manually or via DHCP. So this one is usually called the PIP address, if I'm correct. So these are the special type of IP addresses that we have on top of our private, public. We also have these special IP addresses. Then we move to IPv4 versus IPv6. I think we've discussed the lengths, 32 bits, 128 bits. Address types, unicast, sending to one device, broadcast, every device in the network, multicast, a group of devices. Same here, unicast, multicast. Here we don't have broadcast. With IPv6, broadcast is not there. There's nothing called a broadcast in IPv6. What we have is a multicast or node multicast. If you want to send to every node, it's called the O node multicast. So this is the broadcast of IPv6. Characteristics, IPv4 address depletion, unlimited number of IP addresses. Unlimited for now, but I think the number is too huge. If you look at it, currently we're using 2 to the power of 64 addresses. 2 to the power of 64, I think it's a number I cannot even read. It's way more than trillion IP addresses. That's why they are saying unlimited. But I think in the future, I doubt it will be unlimited. Inappropriate packet design, simplified packet header. If you're looking at header IPv6, it is less fields. Less fields means less processing. Less processing means simplification of transmission header, basically. ARP dependence induced flooding, automatic IPv6 address allocation. I don't know what this is. ARP dependence induced flooding. Okay. This is probably broadcasting due to my ARP requests. Not sure what that is, but those are the characteristics of IPv4 and IPv6. Subnetting. Why subnetting? Right. Now, discussing subnetting. Subnetting is basically a way of dividing a network, a huge network, into much smaller networks. So in this example, let me give my own example why we need subnetting. So suppose you have a /24 network. If you have a /24 network, let's say it's 192.168.10.0/24. That's our network. We know the number of hosts that we have in that network is equal to 2 to the power of n minus 2, where n number of bits, host portion. So if I have a /24 network, that is the network portion. It means 8 bits are from the host portion, meaning the number of addresses that I can have in that network is 254. Now, ndikagadzira a network yakadai so iri /24, it means network umu ndine 254 devices, hosts, if I can say. That's a problem for my networks. Why? Critically, because link irikadhakwa 254 devices they says hadisina connectivity. Mainly because link irikatakwa security wise, then all the 254 devices get attacked as well. So to solve this, we have network segmentation. Network segmentation at layer 3 looks something like this. So I can have two more networks like this, each with 254 divided by 2. Not sure what the answer is, but I can say I can have 100 devices here. I can have 154 devices hosts here. This is a form of subnetting. Subnetting is basically dividing network into smaller networks. I can have 3. I can have 60, 120. If I have 60 here, I have 180. Let's have 60. I'm breaking down network here. So instead of having one network in a 254, I can have multiple networks. Another 60, that's 240. This I can say 14, that's 254, I think. So in this network, ikadakwa mamwe network esanga kushanda. Ikadakwa mamwe arushanda, etc., etc. So the idea behind subnetting is to allow us, instead of having a network which has one broadcast domain, subnetting allows us to break my broadcast domain and to separate, whatever the word is, have more broadcast domains, but smaller ones. More, but smaller. So instead of 254, we now have a broadcast domain in 60 devices. So if I send a broadcast, only 60 can listen to that message. That's the idea behind subnetting. Here, what are they saying? The broadcast domain is too large. Once broadcast occurs, an internal network is overloaded. So if broadcast domain is 65,000 devices, that's a lot. It means you are basically sending a message to 65,000 devices. That's a lot to process within the network. So how do we solve that? I can divide these into 10 networks in a 600 each. 600 is a far much less number than 65,000. 65,600 less processing. That's the idea behind subnetting. A network number is divided into multiple subnets. In this way, the broadcast domain is smaller. Network planning is more reasonable. IP addresses are properly used. That's the reason why we have what we call subnetting. Let's keep this. Let's see if we can have an example of a network that properly requires subnetting. Let me skip this. Let me skip this. Right. Let's solve that one. While solving this one, that's where our explanations will come from. So we want to subnet. What we basically have is a network, this one. So our network we are using is 192.168.10/24. This is what we call a network ID. In this example, we're going to be using it as a range of addresses that we get from our ISP. Paunotenga bandwidth, what you basically get is a set of IP addresses that you can use. So from an ISP, you get that range of IP addresses. Now, that range of IP addresses, like I said, the maximum number of devices that you can have, hosts that you can have, is 254. 2 to the power of n, where n is the number of hosts, minus 2. Why minus 2? I think we'll get into that as we go. 254, that's a huge broadcast domain. We break that down to smaller broadcast domains. In this case, we are only going to be accommodating 30 hosts in one network, 10 in another, 10 in another network. How are we going to subnet so that we can satisfy my requirements at Pama Networks Edo? How we subnet, for me, starts with a table, this one, which is number of subnets, number of hosts. Yeah, let me do this. I think I'll need space here. So I had 10, 10, 30. I think I'll definitely need space for this one. So I think my network that I had, I think I gotta say, just let me see. It's 10, two routers, 10, 10, and then 30. Two routers, 10, 10, then 30. So let me do this. So network I gotta, it's too big. Right, router. We have a network in a 30 here, we have a network in a 10, we have a network in a 10. My IP address is 192.168.10.0, I think. Let me just confirm. We're going to be back here, manage.1.0. So it's .1.0. All right, it's .1.0. .1.0/24. Right. So I was saying the table that I'm going to be using to subnet, it is a number of subnets, then it is number of hosts, then it is prefix length. Right. It is 2 times 2 times 2 times 2 times 2 times 2. Let me see. It's a picture. Right. Times 2 times 2. Then I have 128 divided by 2 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 divided by 2. Then this becomes /25 /26 /27 /28 /29 /30. This one does not exist. Right. So what are we looking at? What we are looking at is a table that we can use to subnet an address which is a /24. So if you want to subnet a /24 network, you can either divide it into two more subnets, which are two networks. And two of those networks, each will have 128 IP addresses minus 2. So this is what we call the block size. The actual number of our usable addresses here is -2. So in this case, it's 126. If I want to divide my network into 8 networks, 8 subnets, I can. Then each network will have 30 hosts, and my mask will change to prefix length /27. That is basically what is being shown per table here. So when you're subnetting, well, you are now taking, for example, my networks arco, you arrange them in the order of the highest. So into the network in a 30, then a network in a 10, I have another network in a 10. Your job is to identify how you are going to divide this so that you address according to the number of my devices are on network. So ndikatora 30, it means I need 30 hosts network here. I come look at my table panapa, don't know which row accommodates 30 my hosts. Row no accommodate 30 my hosts is that one. Then I use that row to form new networks. New networks I'm going to form 8 my networks. My networks antichaforma anotanga near to the parent network 10.1. No parent network 1.0, not 10.1. That's the parent network ish. And instead of taking the parent prefix length, annotate the new prefix length from the row AD. So that's the first network of 8 that I can create. The next network, I add this value here, the block size. So if I add 32 here, I get .32 / 27, 192.168.1.32. Then I add another 32, I add another 32, another 32, another 32, this should be 160, 32, 192, 32, 224, 1, 2, 3, 4, 5, 6, 7, 8. Then if I add another 32, I think I get 256. We can't have a network in a 256. So these are the 8 networks that I can create that accommodates 30 devices. Kana ndatora my networks angu 8. Then from those ones, I get 1. Ndiyo ndinoassigna pa 30 my devices angu aya. 1, 0/27. Now ndasarwa ne7 my networks. Ndakunoti if I want to accommodate 10, what do I do? Ndodzoka pano ndotasa which row accommodates 10. The row which accommodates 10 is probably this one /28. /28, what do I do? I take the second network address, this one, and I subnet it further to form 60 networks, each with 14 devices with a /28 subnet mask. So ndikaitora, the second network is 192.168.1.32, I think. That's the parent network. Ndopatirobvisa 16 maadresses add up. Then instead of /27, I get a /28. Then I start adding this block size to get more networks. So if I add 16, this is 48. If I add 16, 64. If I add 16, this should be 80. You continue adding 16 up until you get all your networks. Then from these networks, I know that all these networks, they accommodate a maximum of 14 addresses. From those 14 addresses, ndopa ndinongoda 10 chete. So I can pick this network 192.168.1.32/28 for this network. I can pick the next one 192.168.1.48/28. And that is all. I have a range of IP addresses that I can assign for all my networks. Then that is basically what subnetting is. So subnetting is taking this IP address, one each, or divide it into 3 my IP addresses, my networks, basically my subnets. You take that one network ID and you divide it into a number of subnets. Moving on. Let me see how much we have left. I think we can finish this one. So where were we? Nice. Nice. Start up subnetting. I think we've discussed subnetting, what it is. Subnetting is basically having a number of networks, meaning a number of broadcast domains instead of having one. And we have calculated a number of examples, one to be specific. In this case, how do they subnet? Let me see. What networks do they come with? This is how they subnetted. It's a bit different from ours. /28, 10/28. And what did they give this one? Subnet 3. Yeah, question mark. I'm not so sure how they were subnetting. I can spend some time trying to figure it out, but I think we've subnetted using our own set of values. Subnetting is the same. Even my IDs akasiyana, but probably the idea remains the same. My IDs are not going to siyana, for example. I'm going to choose a panap. Instead of choosing this network, those not going to siyana things like this. So instead of choosing E 0/27, no going to choose a E kuti ite first network yangu. So meaning panapa takuchinja panapa. Instead of 0/27, ndakuita 128/27. The network still works. So my values are going to change depending on the type of network that you are picking panap, but everything will still work. I think as we go, we have more examples, but for now, hopefully this works as a way yokuthi mukwanise kunzwisisa what is going on here. All right, moving on to ICMP. Internet Control Message Protocol. ICMP is a protocol that is used to transmit error and control information between network devices, playing an important role in collecting network information, diagnosing and rectifying network faults. ICMP, in its simplest form, is what you call ping. I'm sure you've heard about that. A tool which is used to test for connectivity. I'm not ping. So ping makes use of the ICMP protocol. Tikadipisa pichana, you're going to realize that the protocol at not IP is designed as a best effort protocol, meaning you have no way of knowing good information in the. So if you are sending using IP and IP only, I will say have you delivered information or it has been delivered actually. That's not very good in a network. If you are sending information, you need to know is there connectivity between Goro and this information or Akuna. So IP is designed as a best effort protocol because it is needed to have less overhead. So to help IP, kuti tikwanise kuona pane connectivity ere, tinoshandisa ICMP. Example endapa ndo ping. Pakaitika ma-errors within communication yedu, ICMP, that's the protocol that helps with that messaging. Now, as you can see, my errors are actually my codes. My codes 0, type in code. My description, I'll just go through my description. Echo reply, network unreachable. So if you get a code like this, it basically means the network is unreachable. Network here is not on the routing table. Host unreachable. Our host, the network is reachable, but host do Protocol unreachable. Host through per host, but the protocol we are trying to communicate with aripo pahost. Port unreachable ndasvika pahost, protocol riripo, but port ratinofanira kusvikira is not available. So these are just the messages dzinokupa kuti uzive if you are diagnosing a problem. For example, kuti if I get a code yakadai, it basically means kuti device ranototosendera information haritombo panetwork. I think that helps when you are then trying to troubleshoot. Or device riripo, but port harisi kushanda. That helps when you're trying to troubleshoot. So ICMP is basically a protocol used for error messaging, sending error and control information between my network devices. Example, ndoye ping here. As you can see, ping is basically a request which is sent, an echo request. Echo request here, if I get a reply, then it means there is connectivity between my devices. This is an example of a ping on a device. This is a router, a ping on a device. And this is the replies you are getting. So basically, here I've sent 1, 2, 3, 4, 5 requests, and I've got all the 5 replies. The reason why I send a number of requests, because pamwe kutanga inomboregera kusvika, yechi2 inomboregera kusvika, but yechi3, yechi4, you can get responses, and that's how you know kuti pane connectivity. Another example, ICMP traceroute, which is also used to test for connectivity, but this one also adds an element of my hops, identifying kuti pane mahops mangane. I can see my time is almost up. I think I'm almost done anyway. I think we can end it here. Zasara will continue probably in our next session. Thank you for the 3 who are still in. No, 2 actually. Jose Felicitas and Taiwan na Shemushonga. Kana manonoka kuisa assessment enyu. This is a passport.